And I see myself today. It looks like I am live. Yep, looks like I am live. Okay. So, let's do this. I don't think we need that right now. So, let's kill that. I should probably watch my commentos. Got a chat. We've got 4 viewers. Where's my chat? There's my chat. Hello, we're back, boys and girls and people who decline to have a binary gender. Yeah, we're back and we're on the YouTube. I want to point out that I expect that today will be slightly less well attended, given that we're just getting back from the holidays. So we're going to try an experiment, taking advantage of our slightly lower count. If you click over to the Discord and go to chat, so I'm doing, I guess you can't see my mouse. There is a chat in the Discord, so if you want to ask questions today, oh, yeah, hello. Okay, looks like sound is coming out of microphone. Okay, good, I have not been muted. Yeah, so if you jump into chat today, you should be able to ask your questions directly over voice, which might be a slightly different flow. Yeah, okay, so let's, okay. I'm gonna wait for people to start trickling in. Oh, and it looks like we got some in the chat. Curious what happens here. Okay, can someone confirm that they can hear me by audio? Check 1 2. Can someone confirm that they can hear the things that I'm saying in the Discord chat? Yeah, so this experiment is, since
Will you try again?
There we go. Yep, I hear you just fine. So yeah, this since we're down in numbers today, and I think we've kind of reached a suitable number such that it's more manageable to do the chat that we tried out in the first session. Oh. That's interesting. We can hear you, but I can't speak. Gotcha. Okay. Yeah, so we did this experiment in the first session, and it turned out that this is a pretty awful format for anything more than, say, 100, and probably closer to, if there was more than, say, 30, this is probably not the ideal format. But since we're now kind of trickling back down in numbers, this seems like it could be a useful way to have a bit more interactivity in the lecture. So we're going to try this out. And it was suggested in the poll that I shared maybe 2 or 3 weeks ago that we try something a little bit more interactive like this, and I think that's a good idea. So yeah, I think we'll wait another minute or so for people to trickle in before we start. Hope everyone's vacations were excellent. I suppose there's been a noticeable lack in my freestyle booping. So I think that was what we set for the last session, was that I need to make weird musical noises before the start of every lecture. So for the next 30 seconds, I invite you to listen to the sound of me making noises. It's Uncloak time, we're gonna do cryptography. Maybe not quite 30 seconds. Yeah, so let's jump right in. So, yeah, we've been gone for about 3 weeks here, and the last time we spoke, or the last time we had session, there was a focus on secure cryptography implementation techniques. So just to give everyone a refresher, we spoke last time about cryptographic agility, the principle that if you have an algorithm that you depend on for security, it's entirely possible that the algorithm gets proved insecure in some major protocol way. But even just an insecure implementation is something that cryptography authors want to be able to respond quickly to. So cryptographic agility is the principle of basically having a way to quickly respond to potential vulnerabilities in your code. To RNO, who just asked, are we doing a split YouTube Discord discussion this time? So this format, I think, is intended such that if you have questions, you would be... So there's a lag on the Discord. There's a lag on the YouTube. So if you'd like to ask questions, you're invited to interrupt me and say, hey, I would like you to explain this a little bit more, since I think that might be a better format for the number of people that are now in the chat. So yeah, feel free to unmute and ask your questions if you feel inclined. We were going through a couple of things that cryptography library authors tend to keep in mind. The first one was agility, in that you may have a secure implementation even of a protocol, but the protocol may be proven insecure, or there may be incorrect errors in your implementation. So authors do their best to have backup options to switch to if the protocol itself is proven insecure or if there are vulnerabilities in the algorithm. And I brought up the example with SGX this fall, which affected several SGX-based smart contract layers. On the main focus of last week, I would say, was an introduction to type-level programming in Rust. And the focus for this week is mostly going to be about compile time techniques. So we're going to be revisiting that a bit this week. So if you weren't feeling entirely comfortable with that last week, you'll have more opportunities to, or the 3 weeks ago, you'll have more opportunities to revisit that this week. The other main focus, I would say, of the prior session was on not leaking secret information. So ZeroEyes and secrecy are two tools for not leaking secret information. And I would say if you took anything out of last week, it would be that we do our best with Rust to obtain constant time or compile time guarantees about our code. And we can do that with type-level programming. And ZeroEyes and secrecy are two applications of type-level programming and just general Rust API design, such that you don't leak secret information about your code base. We also talked a little bit about Subtle last week, which is a library used or designed by Dalek, who are, I think they're formerly Zcash developers. Now they're doing their own projects, some of them, which is a constant time implementation cryptography library to help avoid common constant time errors in your code base. And there were some other things that we talked about last week, like setting up CI, designing hardware, I mentioned that hardware side channel attacks exist. But the main side channel attacks that we usually are concerned about are, let me just find this guy right here. So the main side channel attacks that we're usually concerned about are timing attacks. So without further ado, let me drag this guy in. So here's a paper from, I think, 2 years ago or so, and it asks the question, why does cryptography software fail? And it came to the conclusion, so 17% of bugs are in cryptography libraries. Most of the misuses are by the users of those libraries. And this is sort of why the type level programming stuff from last week might start to make sense. That the type level programming stuff is trying to answer the question, how do we design these APIs as library authors so that it's literally impossible to misuse our cryptography libraries. So maybe I should have led with this. Most cryptography bugs are because cryptography libraries are overly permissive, that they allow users to use the libraries in ways that are doomed to fail. So when we look at what kinds of libraries or what kinds of errors developers tend to make, the biggest one is plain text disclosure. So that means that they logged or they stored a secret in plain text, basically. And so this is why ZeroWise is a useful library and why secrecy are useful libraries. Is that it turns out zeroing memory is actually hard, but also that people don't actually think about zeroing memory. So I would challenge you to think, if you hadn't heard to zero memory before you started writing cryptography code, you probably wouldn't think about it unless someone specifically told you, hey, your memory is still in the cache, but also in RAM and maybe even in swap. So the most common stuff is usually pretty simple stuff like plain text storing and plain text logging. Secrecy and ZeroWise are basically, they eliminate this entire class of bug. Man-in-the-middle attacks, we kind of talked about this when we were talking about authentication. So the main deal here is that, like, you have these man-in-the-middle attacks. Well, a lot of the time that's because developers hear the word encryption, and oftentimes they think encryption and authentication are the same thing. So they just encrypt, or they do inadequate SSL certification checks. That's the second category of error here goes. And there's a great blog post by Moxie Marlinspike of Signal fame from about 10 years ago called the Cryptographic Doom Principle. And this sort of links back to something we were talking about maybe a couple of weeks ago now, which is the question of authenticate and encrypt, authenticate then encrypt, and encrypt then authenticate. And the cryptographic doom principle is basically just re-explaining the padding attack, which I think we briefly covered. And basically the possibility for a padding attack is eliminated by the existence of basically you can stop a padding attack by authenticating second. Because if the receiver can just authenticate in constant time, then they don't have the problem of, okay, now I have to leak the plain text if the authentication is valid. And that's true even if the authentication isn't in constant time. But authentication is still vulnerable to padding oracle attacks. But it means that A, your receiver is more resistant to DDoS attacks, but B, they're also more resistant to VODNAs or padding oracle attacks. So, and I'll have all of these links in the notes. All right. And yeah. So the third category is brute force attacks. So if we kind of go through each of these, encryption logic error, like this is just like, I would assume like you didn't implement something according to the standard correctly, weak encryption cipher. This means that they probably chose something obsolete, weak keys. There are a lot of caveats when choosing keys, but in general we tend to use like very specific primes or very specific plain text values, such that plain text values and keys don't correlate in specific ways. Hard-coded keys, obviously if you hard-code your private key, then it's going to be in the binary you compile to, so you could do binary analysis on a hard-coded key, and B, keys should be changeable. You should be able to change your keys if they've been used some amount of times. Weak PRNG, I guess we'll get to that a little bit next week. We're going to talk about randomness next week. Yeah, and the last three are just about randomness. So all of these are just kind of like your standard run-of-the-mill, didn't implement the protocol to specification or used a weird or home-rolled sort of encryption technique. So brute force attacks on weird exist. the last category, which is what we're going to talk about the most today, is side channel attacks. So side channel attacks most often are timing attacks. And here's our friend Padding Oracle revisiting again. The whole premise of a side channel attack is basically that your implementation was fine at sort of protocol level, but the adversary who asks, hey, could you do this operation for me, and then respond when you're finished with that operation, the adversary times whether the operation took X seconds or Y seconds, and we had an exercise demonstrating that, and you should have been able to obtain that there was a statistically significant difference between the branching in last week's homework, which I suppose we could get to at the end here. But a timing attack is basically in premise that you do operations in not constant time. The adversary can obtain information about your secrets by asking you questions. Yeah, so that's what we're going to mostly hit to today. What do cryptography library developers think about timing attacks? Well, it turns out that, and this is from a paper from last year's Real World Crypto Conference, most application developers either don't use the tools because they haven't tried the tools or don't know about the tools, or at least half of the cryptography developers don't actively use tools for stopping constant time implementation attacks. And then 38% apparently use tools to stop constant time bugs. And this should be pretty striking to you that a lot of cryptography engineers don't use the tools, haven't tried to use the tools, don't know about the tools. And now you might be thinking, well, what are the tools? So this paper, I'll share it in the notes for this section. But in a nutshell, there are profiling tools for specifically measuring this. And it's not entirely clear to me if this author, after having read, I haven't read the paper through and through, but it didn't seem like the author included basic tools in Rust to do constant time implementation, like the subtle library, which we discussed last week. It does seem to me striking that there are tools here that exist that cryptography engineers don't generally know about or use. So we're going to talk about those a little bit today. And here are the tools. Inline assembly is the tool. Slow clap. Yeah, this is kind of a joke. So a lot of the time, highly optimized libraries will actually write inline assembly. And especially engineers working on very highly reused libraries, like SSL, will often say things like, I don't use tools to tell me whether I wrote constant time code, and he's referring specifically to this paper, though it is not because I would consider the problem to be not too hard. It is more because I took from day one the extreme stance of always knowing how my code is translated to machine instructions, assembly, and how these get executed in the silicon. So if you're writing an SSL library, SSL is like every internet connection in the world is like using some SSL library. So this makes sense for writing a library intended on that scale. And if you do want to continue in cryptography engineering to the point where you expect your library to be used, millions of times, maybe a second, then maybe this starts to make sense. But this is not a reasonable take for most developers. This is a way to design code that I think like you really only will be able to do very slowly, and it also puts you at extreme risk for error. Because this also says, and this is the old C++ joke. The old C++ joke is just be careful. And what this developer is saying is that he's just very careful, and he knows assembly quite well. So going back to this, like the leaky pipeline of developers' knowledge and using tools for testing or verifying constant timeness, there are better things to do than just be careful and read all of the assembly your code generates. And so that's what we're going to get to. So is it true that there is absolutely a place for inline assembly and making sure that you understand the line-by-line assembly instructions that your code outputs? Yes. But there are things to do well before that that probably get you much more bang for your buck. And that's where we get to compile time or constant time implementations. So the maybe very first thing that we've already bumped up against a little bit is generic array. And so generic array is, and you may have heard the word const generics in Rust. It was kind of a big topic. It got standardized in 2020. What a generic array allows you to do is it allows you to declare a vector of data at compile time, as opposed to the standard type that you may have used more, the vec or the string. Strings and vecs are similar in that they are dynamically sized data. They're dynamically sized data. Oh my gosh, how am I forgetting the word data structure? Dynamically sized data structures that live on the heap, which means that the operations that you do on them are A, done at runtime, and B, possibly not constant time. So why do many Rust implementations or cryptography Rust implementations use generic array? Well, it's because until 2020, or midway through 2020, which I guess is now about 2.5 years ago, until midway through 2020, const generics were not a core feature in Rust. So the only way to get these constant time, compile time guarantees about your arrays and specify their size, and that's specifically what this n parameter here is doing, or what this n parameter here is doing. These are equivalent. The only way to get this constant size array, where the size of the array was defined by some type value, was to use generic array. And so we kind of get to this comment in about 2 years ago at this point. Now that min const generics has been stabilized in Rust 1.51, should we begin deprecating this crate? And the answer is no. They shouldn't begin deprecating this crate, because it turns out that using const generics is actually not enough. You actually need constant generics, and another buzzword from late Rust development on the street is that min const generics is not enough to actually do everything the generic array does. And this gives a use case of where generic array was able to do something that min const generics was not able to. And that stopped being true when generic const expressions, that is GATs, generic const expressions recently landed in Rust. I think on the order of maybe 3 or 4 months ago. So now there is actually, as far as I know, no reason that generic array should continue to be a crate. It no longer has its reason to exist because all of its functionality is now moved into the core Rust language. But you're still going to see it pretty much everywhere that you see constant time implementations of arrays that are done at compile time with this sort of syntax, or that syntax. But all of this is to say, why would you use a generic array or a const generic at all? Well, it gives you this way of saying that your struct foo here, it's generic over a type value, which we'll get to in a second, where you can say that foo is completely computed at compile time and never changes again. There's no way to define this constant or this structure at compile time such that bytes actually lives on the stack without using either const generics or generic array. Because you would need to give it some constant value for this n, and the only way to do that would be to use one of those two tools. And the only other solution would be to say, okay, well, let bytes live on the heap and call it a vector. So const generics are a way for you to have structs like foo, where foo has this compile time bytes value that is effectively a constant, such that you can do all of this logic at compile time. And remember that we do this logic at compile time because it A, makes our code more efficient, but B, it's a reduction on the potential foot guns for things that are non-constant time at runtime, or at in our code execution trace. So I guess I have one more example here about how to use const generics, but I think we're going to skip right over that and get to type num. So here is the type num crate. And for anyone curious about what just happened there, I used a DuckDuckGo bang operator, or backslash operator, to search docsrs. Actually, this is worth pointing out. This is great. So if I want to search docsrs, the Rust documentation for any page, I can say docsrs type num, and this is the crate that I want, and we can get there. So that's pretty useful. Neat trick. So usually generic array or mint const generics are used in collaboration with type num, because what are we using with what is n here? This n is not lowercase u size or lowercase u8. It's a type, and u8 is a type, yes, but it's a type with a bunch of different values. We actually just want the type of a single value. Like, for instance, the number 8, we want a struct with a element called bytes. We want this to be a set of an array of 8 u8s. So if we just put u8 there, this would be potentially anywhere from 0 to 255 u8s. So we actually need type num to say specify a specific value in the type system. And so all of these types are basically single values encoded as types. And this turns out to be pretty useful because it means that we can do the stuff that we demonstrated over here with generic array or with min const generics or whatever we're using. It means that we can create these values at compile time and create these constant arrays. So yeah. And on that, I think we're going to, I guess, like, whenever you see generic array, you'll oftentimes see these values like capital U, U128, or capital U, U32. And they're used exactly for this purpose, that usually there is some constant time, compile time operation going on. And that's what those are used for. Yeah, okay. I pulled out a couple examples here. So this example is taking blocks as a function. Hey Jason, I'm recording. Could you not? This function is taking a generic array defined over U8 types and U64, which means that it expects 64, an array of size 64 over 1-bit chunks. So this is in total 64 bytes, right? And then it does presumably some unsafe stuff to compute the hash, I'm gonna guess, of the state and blocks. Then I think we are going to move on to some other stuff that does constant time limitations. Yeah. So the other crate that I wanted to point out here is the I wanted to return to subtle. That's what I wanted to do. So, I got a comment here. I might be mixing generic const expressions with generic associated types. I might be. I'll loop back to that. It's possible that I am mixing something up. But looping back to subtle. So subtle is this constant time library. It gives you several traits and structs that allow you to specify that something is constant time. And we go. So yeah, if we want to see an example in the Zcash pasta curves code base, they implement a finite field called FQ. And if you aren't familiar with what a finite field is, it's a set of integers modulo some prime. So Q is generally the prime here, or P is the other letter that's commonly used. So they're implementing a constant time equals function for the field modulo some prime. And they can use the convenience function CT equals, it looks like here. But with a little bit more granularity on what that looks like, we can zoom into, we can zoom into this blog post where in general when we look at how to do something in constant time, we're usually looking at bitwise comparators as operations. Sorry about that. So yeah, when we're looking at constant time implementations, we're usually looking at bitwise comparators. And the reason this in particular is zero function works is it takes advantage of the fact that if we say take the OR of x and its negative value, the only value for x that will not produce any bits, that is if we think of x as some 2's complement representation, the only value that will not produce a negative in the first place when we OR it with the positive and negative value of it is 0. So this is 0 operation says take the bitwise OR of x and its negative, and since the 2's complement stores the negative bit in the very 0th or first location, then only 0 will fail to have a negative bit toggled in this particular piece of code. And so generally when we're working with like constant time assertions, we're usually looking at underneath the hood, we're looking at some way to use bitwise comparators to say that something is true. This is also true of static assertions, which is a way of putting in compile time assertions about the size or other components of your code. It's a way of saying, in this particular instance, const assert is a way of saying this needs to be implemented on a 64-bit architecture. Let me check that I have that correct. U size, const size of is 4. Actually, I think this is 32-bit. Huh. I guess this is saying, yeah, okay. So this is saying that this can only be written on a 32-bit architecture. Because the size of U size is 64 bits on 64-bit architectures and 32 bits on 32-bit architectures. So I think the size of is, oh no, okay, so here's what's going on. It's just greater than or equal to 4. So I guess that then I misread this earlier, and I'm honestly not sure what this does now. Because this says that we need to assert that the architecture is either 32 or 64 bits. Which apparently, this implies that some architectures are less than 32 bits, which I did not know. So I guess we'll skip over that. So yeah, the whole premise here of constant time implementations usually is somewhat reducible to if you are doing something with secret data, anything that you wouldn't want to leak in a timing attack. Your sort of first reach in tools are these three crates: generic array or constant generics, type num to encode specific values in the type system, and the subtle crate for doing constant time comparisons. And if you want to do constant time assertions, the static assertions crate also exists. Though I hadn't actually seen it used before I started looking at this particular library. So, yeah, moving back in. So there are a couple of other examples in this blog post. It's a good blog post for explaining where the bitwise comparators make sense. And the reason that they do these bitwise comparators is that oftentimes comparisons compiled by this compiled operation, if you were to do it as not a bitwise comparison, the compiler might say it would be more efficient to short circuit as soon as I find a single bit that doesn't satisfy this value. But as you probably now know, as soon as I find a single bit that doesn't satisfy is a way to leak timing information to the adversary. So then we get to maybe the second major topic of this lecture, which is traits. And I suppose this is a pretty straightforward topic, but this more has to do with good software engineering design. And in particular in cryptography, it's common that we want certain common things. So pulling back at the subtle implementation, a lot of these are traits. And these traits can be used as flags as to whether a particular object, your struct or your enum, satisfies some trait, that it can be compared in constant time, or that it can be conditionally selectable in constant time. So the Rust crypto organization maintains a whole library of traits that are fairly common that you can use to basically say, this is an elliptic curve and it implements this particular flag. So other users of that crate will know that it's intended to be used as such. And the reason we do this is specifically kind of going back to this paper. Why does cryptography software fail? Well, this is Rust's answer to 83% of cryptography libraries misuse or inevitably get misused. So traits is the answer Rust brings to, well, how do we stop crypto misuse? And so taking as an example here, the crypto RNG trait. The crypto RNG trait is a very simple trait. In fact, it's so simple that it takes literally no lines to define, or one line to define. So the crypto RNG trait basically just exists to say there are lots of ways to implement a random number generator, but for many applications, a random number generator is a bit overloaded, because when a non-cryptographic operation or a non-cryptography application says, I want something random, what they actually mean is they want something uncorrelated. They want an uncorrelated string of variables. And it doesn't actually matter whether it's predictable, the algorithm for generating these uncorrelated values. But when a cryptography library says, I want something random, they mean I want something that is unpredictable. So randomness is overloaded here, and I think this is a good distinction, that if you're specifically talking about a cryptography use case, we're thinking uncorrelated, or sorry, unpredictable is the cryptography use case. But when a non-cryptography library says, I want random, they usually just mean, I want uncorrelated. So what does this crypto RNG trait actually do? Well, it doesn't define any methods because a crypto RNG is going to look fairly similar in API to a non-crypto RNG. But it's a way of saying if I want to declare that my RNG, for instance, the operating system RNG, is cryptographically secure, I can do that by implementing this trait flag, crypto RNG. And that's all it does. It just says implement crypto RNG for OS RNG because OS RNG is cryptographically secure. And I think this is based on, depending on what operating system you're using, this is valid for getting some random values from your operating system, which is achieved in different operating systems in different ways. And here's another example of it, implementing crypto RNG for reseeding RNG, which is another RNG in the Rust random library. And these are all empty trait implementations where this where block is just to satisfy the requirements for reseeding RNG. But at the end of the day, implementing crypto RNG is just basically a flag saying that reseeding RNG is safe to use for API consumers, saying that, yes, this is a cryptographically secure RNG. So, yeah. Let's see. Did I have anything else in this section? I think that was about it. Yeah, so I suppose the takeaway here, or the in a nutshell, is that when you're implementing, whether it's an AEAD or a hash function, there's usually going to be somewhere in often the Rust crypto library, or at least somewhere in the existing set of already out there traits on crates RS or whatever. There's going to be traits that might be useful for you as you implement whatever it is that you're working on. And if you're working on something that's relatively recent, like zero knowledge or multi-party computation, the trait is the shape of the interface. And so when we come to define a trait in Rust, it's sort of like standardizing across the interface across all of the libraries that might do that thing. And so this is effectively a community-held standard. This is basically what the Rust community standard is going to look like. If a trait is used, then that is the API that everyone will expect to consume. If that trait basically becomes the go-to of what does it look like to be an encryption algorithm, or what does it look like to be a async stream cipher. All of these are sort of the community coming to agreement about what APIs should be expected for a inverting function or whatever else. Which is to say that if there isn't one of those, then it's worth having a conversation about what a standard API could look like so that there would be interoperability between different libraries. So I want to move on to the last topic in this lecture. And this is frankly the topic that I know a little bit about, but not as much. And this is computer-aided cryptography, where we use computers to make cryptography. That's a joke. But the premise here is that the premise for computer-aided cryptography is basically, can we use formal languages when designing protocols and when analyzing implementations of protocols to automatically obtain proofs of the security properties about a protocol. So common examples of provers, or in particular auditors, are the most likely to use provers when doing audits of your code. But there's also ways to use provers up front when designing protocols. And there are now a handful of libraries for basically saying, is this a secure protocol, even before you've implemented that. There are also tools for analyzing the assembly of an algorithm, or analyzing the implementation of an algorithm. So the takeaway here is that this is kind of an area of active research. Most of these tools are on the order of 5 or at most 10 years old. Veil and Jasmine are two relatively recent efforts in doing formal verification at the assembly level. The Z3 prover is another well sort of established prover for verifying theorems about a set of programming languages, including Rust. And I think that I honestly don't know enough to say whether these will move more into the sort of standard set of tools for cryptography developers. But I wanted to bring them up as a sort of topic area that you should be aware of, and that auditors in particular are looking into how to use these assembly verification tools and protocol design tools to make sure that their sort of the code that they're looking at is secure or designed without errors. And it turns out there's a lot that you can actually do with these formal verification tools. And I suppose that this would also be a good time to mention something that came up in the chat in the last week, which is the Flux type language that was introduced towards the end of last year, I guess in November. And this was actually a fairly fast turnaround time from paper to working implementation. I think I saw the paper come out maybe only 6 months ago, so I was pretty surprised to see that it reached a production level implementation this quickly. The Flux language is maybe the most accessible of the set of, I guess these are more referred to as formal verification languages or assembly languages, or assembly verification languages. Flux is a tool for you to say, do a lot of the type level constraints that we introduced last week in the course of talking about Will Crichton's type level programming blog post. Flux is a way to say, put a decorator on the function that says, I want this function to assert that something is true, not at runtime, but at compile time. And this should sound reasonably familiar because we've been harping on we've been harping on compile time assertions basically the entire hour. But B, a lot of these assertions should remind you of the things that you might have seen last week when you were looking at the type level programming blog post by Will. So this is kind of another tool that I expect to sort of enter the common set of tools used by developers to basically say, prevent, there's a buzzword here, make bugs unrepresentable, or make invalid state unrepresentable. This is a new tool for making invalid state unrepresentable, in that assert 2 plus 2 equals 5 is something that would usually fail at runtime, but Flux will make this such that assert that 2 plus 2 equals 5, this function fails at compile time, which means that the compiler is actually doing this execution of 2 plus 2 equals 5. Now, I should make a final caveat here before we tip over to questions and maybe discussing last week's homework. Using all of these compile time tools does mean that your compilation time might be longer than it otherwise would be. Because obviously your compiler is asked to do more work by these compile time tools. So there are ways to minimize your compile time. And I will leave out this blog post written about 2 years ago on things that you might be concerned about for using these tools if your compilation times get to be kind of long. And I want to wrap up here on this blog post, which is one of my favorite blog posts. It's the Grug-brained developer. And so I'm just going to read 2 quotes from this post. And the Grug-brained developer is kind of this post by an anonymous developer speaking in somewhat caveman speak about how to do software development good. And it's sort of a very modest post and a very sort of self-aware post. Grug always spent time in new place learning tools around him to maximize productivity. Learn tools for 2 weeks make development often twice faster, and often have dig around ask other developers help, no docs. The point here is that there's tools around to help you do things, and I don't think I honestly need to beat this point home because you all are here doing sort of learning on your own accord about cryptography engineering. The point here is that like tools exist to help you do these constant time implementations and these compiled time checks. And the second point sort of stands in direct contradiction to it about type systems, is that some big brains think in type systems and talk in lemmas. The warning here is these tools are not simple, and there is a danger of sort of forgetting exactly what you're doing, or even if you know what you're doing, there's a danger of communicating what you're doing to other developers, because type-level programming is something that is very useful in cryptography, but most developers probably won't touch type-level programming in their entire sort of development career. So the value of being able to explain exactly what it is you're doing with type-level programming, whether in comments or in documentation, is quite significant. And so I would stress, as a sort of like leaving out or on a trailing out note, the danger of abstraction being high is sort of one that I think we accept in Rust, and that we work in this language because it guarantees secure implementation. It guarantees correct compilation without a lot of these fears of runtime memory bugs or non-constant time implementations. But the danger of getting too abstract with your implementation is certainly a real one. So I want to leave out there and ask if anyone in the chat would like to ask questions about this week's lecture. And yeah. I forgot there was a huge lag between the YouTube and the Discord. You're welcome to I should just. And you're welcome to unmute on the Discord chat and ask over voice. All right. If there are no questions, I will move on to discussing the homework from last week. 3, 2, 1. Okay. Let me pull up the homework from last week. So, moving this right there. All right. Hope this is large enough. So last week's homework, there were a couple of things. The main thing was getting a little bit used to getting hands dirty just a little bit with type-level programming. And the very first exercise was to say, implement a state machine that demonstrated using phantom data. And phantom data, in case you haven't seen phantom data before, is a useful parameterizing struct in Rust that never takes on any value. That is, phantom data is a compile time tool that that doesn't have any effect on the runtime. And it's mainly a way of manipulating type systems. So in this case, we're manipulating type system to be parameterized over some state, mutable or immutable. And if I pull up the blog post, blog post that Will Crichton has here, we use type data as this marker of what state our struct is in. But at runtime, it gets entirely compiled out. And I want to pull this up especially to highlight one thing in particular, is that a difference between the implementation that I give and Will Crichton's implementation is that he implements these types as high-sec and low-sec structs, whereas I implement them using this useful handy-dandy tool called tylift, which is a way of saying that if you know that your state is going to be an enumeration over some structs, then the way to do that most effectively is to say, well, I want to encode this as a enumeration at the type level. And tylift is a way to do exactly that. And the code it generates is, it will generate a module that has, as before, these structs mutable and immutable, as you would see on the right side with structs high-sec and low-sec. And they are optionally parameterized over phantom data, which that stays an empty phantom data unless we actually put stuff inside of these structs, like I could put some data that these structs hold. And basically we say, we now get this type called my state. So we're going to implement the trait my state for immutable. And now when we code down here, we can say in my state machine, where S is either of my state is the enumeration here. S is one of the values in my state, mutable or immutable. Then we say the Y value of my state and the phantom data of my state is whatever the parameterized state will be. So if we use this in a if we want to make this particularly ergonomic to use, we can declare a type alias for mutable state machine, which is my state machine in the mutable state. We'll use this in our API caller down in test in a second. We're going to implement several methods for this state machine. We're going to get a new mutable method, which returns a state machine in the mutable state. And the way we do that is we very simply say, declare this function signature to see new mutable gives me a my state machine in the mutable state. And we declare my state machine just like we would expect. The phantom data doesn't get any arguments. It's just this sort of flag that phantom data represents. And this gets entirely compiled out in the actual execution of our code. So in runtime, there is no phantom data component of this. This is purely for compile time record keeping. And we'll implement a getter, get y, which returns the value of y. And this should be available for the struct in any state. So we have it parameterized over S in any state. But then there are some methods that we only want available in the mutable state. And then there's a method that we only want available in immutable. Actually, I implemented increment in both mutable and immutable. But in immutable, it gives this warning message that it can't increment. So in the mutable state, we'll give it the methods increment, freeze, and reset. So increment, as it's mutable, it will increment y. But if it's in the immutable state, we're going to say that it's frozen forever and it can't increment. It's done. We're going to say freeze, which is a conversion from the my state in mutable to my state in immutable. And we just say create a new state machine with y equals y.self, and phantom is phantom data. And this method is the equivalent of a unsafe method in the blog post. So what this method is it's saying it will transmute the representation of channel in the blog post from receiving state to sending state. This is effectively equivalent to that, but without the unsafe block, which I remember there was some hesitation to jump right into using unsafe, even as we said that we're aiming for guarantees about the correctness of our code, which those are reasonable concerns. And there is a totally safe way to do this. It's just consume state and then return an immutable version of that state. And then when the state is in the immutable version, I mean, we could conceivably say have an unfreeze or unlock function in immutable that says, okay, now send it back to mutable, and it would look basically exactly like this. We would just go down here and say we wanted an unfreeze function, and we would just have a identical function that looked like unfreeze, like this. And now we have our hunky-dory new unfreeze function. If we called that for my state machine in immutable, we could say call unfreeze, and then this would actually compile. And yeah, and then that would go all well and good. But if we took this out, then this will actually fail to compile because the my state machine doesn't have a reset function in immutable. So you literally cannot call the reset function, which would mutate the state, since the state machine is not in a state that actually has a reset function. And this is what we mean when we say that we're implementing APIs that are implementing APIs that are impossible to misuse at the type level or at the compile time guarantee level. So then we can say test state machine. And that'll take a hot second, so we'll just hide that while we continue. So that's how to use type level programming to get these guarantees about your implementation, such that they are literally unusable, or literally unusable, such that they are literally impossible to misuse by using these sort of compile time type level tools. The next one that I wanted to demo is that we can use another compile time tool that is in the Rust core called features. So if we say have a malicious feature, say if the crate is compiled with this feature malicious, then return the string not good boy. Otherwise, just return whatever the var that was passed. So a way to use this would be to say let out be good boy, and then if evil is compiled with the malicious feature, then it will return not good boy, but if it is compiled without the malicious feature, it will just return out itself. And then we can test this down here and say test good boy, and before we do that, we can see that the previous test that we just ran passed all of our things. So now we're going to say test good boy, and test good boy in without the malicious feature passes. And if we go features, let's see. And we said in our test, if the feature malicious is compiled, we expect that the output of this will be not good boy. And we could even say move all of this out to another test and say if we wanted to do it this way, do so if we said we wanted to compile a test that should panic, then we would say let the output equal good boy as before, and we would say if compiled with the feature, or actually let's just say assert equal output, and I guess we're going to say good boy. Just move that here, delete these lines, and say that this only runs with CFG feature equals mal. I think this is it. And if we run this code, we should expect that both of these tests get run. And if the features, okay, if we test these, both of them will pass in the honest direction. But if the, let's see, if we compile this with a feature mal, then this test gets run, and we expect the output good boy, but we actually get the output is or not good boy. So that would be one way of saying, using a feature to say, let's test that something is true with an honest compilation. And that technique is particularly useful if you have a party that could be Byzantine that is running your protocol. So this is particularly relevant for, I think, this audience, who I think is largely composed of a sub-audience that are sort of blockchain oriented. Generally, we design protocols such that even participants of the protocol could turn out to be evil or malicious or colluding. And that feature approach is particularly useful because in, say, a two-party protocol, we get to assume that everyone is authenticated, or we get to authenticate everyone. And then we assume that everyone who's authenticated is honestly behaving. But in a sort of multi-party protocol, like a blockchain, oftentimes even authenticated parties could be easily misbehaving or offline. So it's a technique specifically useful for that particular case. And then finally, we get to the last major exercise of this homework set, which is to, you say, do some branching. And the way to, I mean, this is fairly straightforward. We just say, let a constant be our secret value and create a secret vector composed entirely of the constant, and do some branching and see if we can observe a difference. And it turns out that we can observe a difference. The left path, that is, if val is secret, that means that all bits were compared from secret to the constant. The left path is going to take longer since it couldn't short circuit on whatever values were present. Versus if the value, I suppose I should probably go over to benches here. Yeah, so the data that I actually used here to run these, or to run, that's definitely not it. Run the left with secret, run the right with 0, run the left with secret vector, and run the right with the same vector of value 0. The left vector is going to never get to short circuit because it needs to compare every bit. The right value is going to short circuit every time because it just says the first time I see 0, I'm good to go. Same thing is true for v left and v right. And there appears to be some sort of optimization that the compiler is able to do because the difference between 1.9 and 1.6 is significantly more than the difference between 361 and 365. So I'm not entirely sure what the compiler is doing there. I would have expected this difference to be roughly the same. That is, this is a difference of maybe about 30%, that the left is 30% slower than the right. This is less than 30%, so the compiler is doing some compiler magic here. But we can still very much see an observable difference in the left branch, which was allowed to, or the left branch, which had to compare every bit, and the right branch, which very much didn't. And this is a sort of example of how we would start setting up a timing attack. So if we were actually trying to do a timing attack on our code base, it would look basically like this. We would want to benchmark whether we could observe a statistically significant difference between value A and value B, and then iteratively reduce what possible values value B could be based on that timing. So yeah, I'm going to open this up one more time for questions in the Discord before we call it a day. Cool. Oh, I see it unmute.
Can you hear me now?
Yep.
There we go. I thank you again for the course. It's been super fun following along. I have a question with respect to kind of type programming part.
Yeah.
And I think I'm in the forest from the trees right now. Like I understand how it's implemented, but I guess where I'm a bit confused is kind of its relevance to cryptography or like to the things that we have been learning so far. Not as a criticism, I'm actually just generally curious like where it's commonly used.
Oh, it's commonly used quite a bit. So the are you asking for a specific library, or are you asking why it's used?
Probably for a specific library or like a specific example that might use that.
Yeah, I can get back to you on that, but it is.
Okay.
I don't have one specifically right in front of me, but I can pull up a couple of examples to drop into the chat afterwards if that sounds like a good deal. But
No,
I will
that's
take just a
perfect.
second to say the reason we use it is because it gives us these compile time guarantees. And if we are looking for ways to basically get constant time compile time guarantees, as well as like other guarantees that our code is correct and not exploitable. We're looking for as strong as tools as we possibly can to come up with basically ways to make sure that our code is correct, and type level programming is a very powerful tool to do exactly that.
Awesome. Thank you. Maybe just an elaboration there. You mentioned for the constant time evaluation,
Yeah.
and that we can write type programming and enforce that via the compiler. I guess I'm a bit lost there as well. Is that just like we introduced these generic arrays? Is that like an example where type programming is used for that?
Yeah, exactly. So generic arrays, the whole premise of generic array is that we want to assert that the data structure is going to be constructed entirely at compile time, as opposed to there being maybe timing information leaked from amortized growing or shrinking of a data structure that lives on the heap. So vectors and capital S strings in Rust live on the heap, but the square brackets arrays and lowercase ampersand s strings live on the stack. So if the object lives on the heap and say has a growth operation or is just generally slower to begin with, there are things that can be inferred about the code base from a clever attacker looking for potential like places to look for memory leaks, or sorry, not memory leaks. But if something is on the heap, it gives the implementation a more wide surface for misuse, because even if the thing is not declared as mutable, there's just more sort of like memory guarantees that we can eke out by saying, let's make this a constant time compile time sort of value. But specifically with the case of, I was going to pull up constant time implementation stuff with the subtle library. Let's just go. Yeah, with subtle, we are given these 5 traits. And if we look at these 5 traits, just picking up constant time equals, for example, which is maybe one of the more useful ones, it gives us this one method, ct equals. And if a value, like your whatever struct you choose, implements constant time equals will do actually the work of the constant time comparisons that there'll be examples of in the NCC blog post that I have right here. So yeah, in this NCC blog post, the author is doing his constant time implementations by hand. And the trait actually gets us pretty far in that it's going to do all of these constant time implementations basically in this, or I guess I'm lying a little bit. The constant time equals function says that it's still on the developer to do the implementation of the constant time equals function, but declaring that the equals function should be constant time in the first place is to say that this gives us a sort of tool at the API level of saying, we will not implement equals for this struct, but we will implement constant time equals to represent that whatever the implementation is should look like this, as opposed to a short-circuiting equals, which is more common. So I suppose that's like maybe the sort of like standard level tool is like using traits like that. But the type level programming tool is to say, as we demonstrated with my state machine, some methods should only be available if your state for whatever your struct is in a particular like substate. That is, there are some values, like for instance, like there are some unsafe prime values that your state machine should never be able to obtain. And we can use type level programming tools to say, well, make those states unrepresentable by declaring our states as not including those as even possibilities because they're not in our types. And so that's the sort of, I think, intuition that the type that we want to define can exclude incorrect types by making them unrepresentable and encoding our state transitions between states carefully so that it's literally impossible to represent invalid types. I don't know if that was helpful. I might have been a little bit too long-worded.
That was incredibly helpful.
Okay.
So thank you. Yeah, no, that actually solved a lot of the uncertainties I had around it. So thank you.
Great. What was it? Library that I looked at a while ago that I'm trying to think of. It was like integers without zero. Is it that? Any other questions before we wrap up?
I'm just not sure I understood the cons generics difference between, so the difference between just defining a normal array and using the cons generics.
Okay, yeah. Using a what was the first thing you said? Using a non-zero array or a non-constant array?
Yeah, so just defining a constant length array on the stack and using cons generics.
Right. So you actually can't. So suppose that I wanted to go down here and say let a equal. Let's go up here and say here's a struct. And I want array to be I32 and sure, say 10. So, gosh, what's going on here? It should be fine. Expected sync. Oh, okay, right. So we can do this very simply by saying, here's my struct, we can do this, and this is fine. But this is not going to be constructible at compile time. So if we say that we want to construct const C my ass, get it? I'm very immature today. Let's say it's going to say that I guess that did actually compile. I'm gonna have to get back to you on that. Thought that this would fail. But in a nutshell, my model here is that you can use these const generics to say basically you should be able to declare a struct. This might be because const generic what was it? Const generics. Yeah, this might be because const generics landed. But you know, I think probably the safe thing for me to do here would be to just say, oh, let me get back to you on that. But in a nutshell, a lot of our techniques for constructing compile time guarantees rely on being able to encode that a type is either a singleton type like this capital U, U8, and geez, it's in there somewhere. Yeah, let me get back to you on that. Because I think my demo here has failed and now I'm struggling. Any other questions? Okay, so I did find the struct that I was thinking about in standard. It's a non-zero integer value. There are instances where we specifically want a non-zero integer. And the non-zero integer value under the hood uses type level programming to say, make the zero value unrepresentable. So if you peel back the curtain on non-zero I32, you will see that it's basically the same as an I32, just with the addition that the value can't take on the value 0. So I think I'll put that in the notes for this week's lecture as well. And with that, I think we're a little bit over time. So thanks everyone for coming, and feel free to give any feedback about the lecture, and look forward to seeing you next week. Bye.